Next is exercise 19. Exercise 19 is an interesting one, also about Lenz's law. It says determine the direction of the current in resistor AB in this figure under three separate conditions. And so we have coil A wrapped around this conductor there. It has resistor R, and the EMF is starting here, and there's the switch. And so the current, under normal circumstances, when the switch is closed, will travel in this direction, wrap around the coil, come back down this direction. And so it's asking, and in current B, it has no real current until it's induced by magnetic field of the other one here. And so when nothing's changing, then there's no current in B at all. So it's asking, first, part A, the direction of the current in resistor AB when the switch is open after having been closed for several minutes. And so we can assume that regular flow that we just talked about earlier, and the switch is opened. When the switch is opened, the flow will decrease and stop on the side in coil A. And so when we consider the direction of the original current, it's going this way and wrapping around like this. If you follow my fingers when I wrap it, you'll see it come from the top here and go down to the bottom and wrap back up around. And so that's the original motion of the current. It starts to decrease when we when we open up the switch. And so its change in current is going to be this way, meaning that the induced currents and EMFs around it will be in the opposite direction, which is the original direction of the current. And so we carry that over to where B is, and we wrap it around. And with B, it's interesting because when we are following current of this direction, we have to follow the wrapping of our fingers more than the point of my thumb. And so as I wrap my fingers, it comes down from the top and goes under and back up around this way. So it's actually moving to the left at the top here, rather than to the right, which might be easy to assume and to get mixed up. And the difference is because of the different direction of the wrapping of the coils. And so it goes down and travels from A to B. And that's the answer for A. And then B, it asks, under the condition, the direction from between A and B, under the condition that coil B is brought closer to coil A with the switch closed. And so we assume that original regular flow in coil A and coil B is being brought towards it, which means that the magnetic field, in a way, is increasing as it comes closer to each other. And so it's moving in this direction, meaning the induced EMF must oppose it in this direction. Now when we look at it moving in this direction, we see that it's the opposite of our previous answer. It's going to wrap up from the bottom and around the top in this direction using the right-hand rule there. So it comes down and runs from B to A and back up and around. And so that's the answer for part B, is B to A. And that resistor on coil B. And this is kind of nice because it's easier than trying to think of clockwise, counterclockwise with how complicated it gets with these coils. Not necessarily very complicated, but it's easier to visualize with the resistors at the bottom, so I'm glad it's phrased this way. Last condition, condition C, the resistance of R over here is decreased while the switch remains closed. And so if the resistance is decreased, that means the current here is increased, which means its magnetic field is increased in its current direction. And so the induced EMF and current in coil B must oppose it again. And then we get the same as we got to answer B, to where it's traveling from B to A.